Welcome back from lunch. I think you are quite familiar with the term ZFS and openZFS, and who uses this file system on a daily basis? Please raise your hands. Well, 1, 2, 3. Okay, 4. Okay, not that much. So we brought to you the best speaker about openZFS, the contributor. So please welcome George Melikov. The stage is yours.
Hello. Okay. Hello, everybody. And today we'll speak about storages and how to deal with its problems via not so default file system, ZFS. And as a start, I want to introduce myself. I work at VK Cloud. We build not only software-defined storages here, but software-defined networks too. And unfortunately, we don't have ZFS yet in production, so I'm here in the role of openZFS contributor since 2016. That's because I love my data really much. And that's why my notebook is, my laptop works ZFS only. So today we'll speak about problems we need to solve when we build our storages. The first problem is scalability. We can't work even on one hard drive. So after that, we need to deal with some faults. So our hard drives will die someday. After that, we may have some disasters. So we need to deal with it too. And we don't want to pay much for our storages. So we need to deal with its cost. And after all, we don't want to pay much price as a staff too. So this will be our topics for today. And as a start, I want to give you some history. ZFS was born 22 years ago. It's a pretty mature file system nowadays. It was born in Sun Microsystems and was open sourced in 2005. Unfortunately, it has a long and not so good history because in 2010, Sun was acquired by Oracle, and unfortunately, the source code was closed. So after that, we will speak about Fox only. And because we don't want to make different file systems across our forks, we will speak here about openZFS organization. Its code base now can give us builds not only for Linux today, but for FreeBSD too. So from one code base, we have at least 2 open operating systems now. And I hope that in the future, another forks will be here too. And that's all for history lesson today. Let's speak about scalability after all. I want to start with the question about locality. We usually have 2 types of systems. We have a centralized one, when we have our hardware just under us, we have our hard drives just under us, and the latency is pretty low here. And another type, distributed one, when we have many servers across network with many clients, and they come to each other via network. And so our latency will be at least latency of our network. But on the contrary, centralized one can be scaled well, because of course we can build some mainframe, it will cost us a ton, and we may scale it somehow, but unfortunately one thread won't be scaled in this case. But contrary, in distributed one, you may build and scale your system indefinitely if you have appropriate architecture. You have different examples from this conference, for example. So the thing is that we don't speak only about storages here. We speak about databases too, because file system is a storage, is a database for files. We have some keys, we have some data, that's all. And let's look at example, database on database. So we need some storage under our high-load databases. Many of us have some high-load databases because, after all, data is our business usually. Databases don't want to deal with raw storage and many disks. That's why we need to build our storage here. And we need some, for example, RAID array. And we need to deal with space efficiency, with space capacity, and with I/O throughput here. So we can use some hardware or software RAID array. Let's look at it from the Linux side. We may have some MD layers here, and use it via mdadm command, so it's pretty alias to it. We may want to use some logical volumes via logical volume manager LVM, and only after that we can create our file system on top of that. And each of its layers have to be managed somehow. So we need at least 4 of them. We need to manage our disks, we need to manage our MD layer, we need to manage our LVM, we need to manage our file system after all, and check it for consistency, etc. And let's compare it to the ZFS. The major point here is ZFS is not only a file system, it's a volume manager too. So you don't need any other layers. You can just create ZFS pool, one ZFS pool, and add some redundancy there. We do it via VDEVs, virtual devices. So you can create some virtual devices as mirrors, the cheapest one. You can create some RAID 5 analogs called RAID Z, or more extravagant ones as distributed RAID. But we have another example. We don't want only to deal with our capacity problem. We want to deal with our objects count problem, because we may have small files, but we have a huge ton of them. So it is equal to us as metadata IO. And you don't want to have your ls command works from several minutes up to several hours. So we want to do something with that. And in ZFS, we can use a special virtual device. It's called special. We can send all of our metadata to it. So let's just have some fast NVMe drives, make it redundant, and that's all. And it's not a cache, it's not tiered storage. It's only in the last position of our metadata. So our hard drives will be absent of metadata I/O. Okay, we can scale somehow, but there is a problem, resiliency. Several years ago, I have read an interesting story from the great science fiction author Stanislav Lem. And there I've learned about ancient Greek goddess of inevitability, Enki. And the point is that it's an interesting myth, but it's not so different from the real world, because in real world, your hardware will inevitably die. That's no other way, unfortunately. Your hard drives will die, that's just statistics. Your HBA adapters will die, and you want to die it instantly, not in several months, because while it will die in several months, it will corrupt your data, and you don't know about it. Your motherboard may die, your memory may die. Many of us knows about ECC abbreviature, but even it can't help us sometimes. Your CPU may die too, and your CPU has some memory in it too, which is exact to RAM here. And even wires to your hardware may give you problems. The fun thing is many of our issues in openZFS tracker is not about openZFS bugs, it's about hardware problems, because ZFS can highlight you them. And some of them even about bugs in kernel itself. Let's talk about interesting statistics. Many of us know Backbase. They have a large fleet of hard drives. And they have an interesting statistics that annual failure rate per year is nearly 1.5%. So in each 100 of your hard drives, it will nearly guaranteed that 2 of them will die in a year. And even more, even manufacturers guarantee you that you will have some read errors per some size. For example, for SATA hard drives, it's nearly 11 terabytes per each read error. So you should not build nowadays any RAID 5 arrays from large hard drives, for example, 20 terabytes, because you can't rebuild them. They will fail on rebuild. Let's dig deeper. The easiest and the cheapest way to have some redundancy is mirroring. So we have several copies of our data on several disks. And the case when we lose one of our disks is not the worst case. It's the usual case for us. The worst case is a power failure for us, because the write is not atomic. By atomicity here, I mean any operation which succeeds at all, or not succeeds at all, so we can compare previous state and the next state. There is no intermediate state. And unfortunately, when you write to your disks, it's not atomic. You will have pretty seamless data, but they will be different, and you need to know how to find the right one, the latest one. Let's look at another example. We may have a RAID 5. It's more cheaper in space. It's more space efficient. It usually works as you have some unique data across your disks, for example, first and second, and you have another disks with the parity data. We can count parity data just via usual XOR. So you can see here that the third picture is nearly the same as first and second. So in the worst case, when we lose one of these disks, we can count its data from the XOR operation. But it's the same worst case with a power failure, but it's worse here. We failed drive, we failed power, and unfortunately it's not atomic, so we have our parity a little bit newer, for example, otherwise our data. So when you try to compute your first disk data, you will have another data. And we should not forget about our friends from space, higher energy particles. They can come into your memory cell and make a bit flip, so your 0 becomes 1. And there are two interesting examples of this case. Your speedrunning, in your speedrunning, you may jump not by 1 meter, but by 10 meters, and you will be the champion of the world. And the second, more pragmatic example, you may have elections, and some of your candidates will have another million or billion votes. You don't have such situation. Because of that, you may want to check for your integrity and consistency of your data. The usual case is to compute some hashes. And the default file systems don't compute hashes, unfortunately. You may use another layer called MD integrity, and it will do for you. In ZFS, we're not so different for a start. We will compute our hashes from our data too, and store that and point us to our data. But the magic begins here. We will compute hashes of our hashes. And after all, we will have the major hash, which stores in UB block 1, which is pointed to our whole file system. So we have only one hash, which tells us if it's okay, if everything's okay with our data or not at all. And if you have some redundancy, we can self-heal our data. So if it's 3 midnight, you have some faults on one of your disks, ZFS can self-heal it, and you will know it only from stats of ZFS, not from production degradation. And you can make a ZFS scrub. It's an operation where you read automatically all your data and compute checksums. And this tree called Merkle tree. I don't know if someone knows Merkle tree, but I'm sure you know it because many of us use Git, and Git uses Merkle trees. And it's not the only analogy here. In ZFS, there is a Git commit analog too. They are called transaction groups or TXGs. We have branches too. They are called clones or snapshots. And at last, we have staged files too. They are on just in-memory directive write buffer. And that's another analogy where I think that ZFS is an interesting database for files. And not only for files, I think ZFS is a Git in file system world. Okay, we know how to deal with faults and check for consistency, but unfortunately we may have some problems with our application logic, or even our data centers may die. So we need to make backups. And the most naive way, just to use tar archiver, just to have some archive with our data. But the thing is that you don't want to do it naive. You need to deal with data races somehow, because in the background, your production database is working. It writes something up, and your backup will be garbage after all. That's why we need some atomicity in our backups. And the common way for our storages to do this is to make some snapshots. And it's in ZFS, snapshots are nearly free. Let's look why. ZFS is a copy-on-write file system. What do you mean here? From the start, we write much more metadata than other file systems. And to write even one bit of data on our previous blocks, we need to create a new blocks. We won't overwrite data at all. It's a no-go for us. And now we have some state where there is a new data, but we don't have some metadata on, pointed at it, so we don't know about it yet if we lose our power. So we write some metadata. And after all, on this picture, you can see two states of file system. The first state which points at UB block 1 and the second one. So in any problems with your UB block 2 and the new state, you can just use the previous one. That's why UB block writing is atomic for us. We won't overwrite our data at all. We won't write it. We will write it only once, and it's pretty atomic. And in the future, sometime, we may rewrite our older data. They are not needed now. And the point is that we can make a pointer to our previous state and tell ZFS, please don't just delete it. It's mine. And it is a snapshot for us, just all. That's all. And I have a great question for you. Is snapshot a backup? Please heads up if you think so. That's pretty great. That's pretty great. The thing is, it depends, because you may have a local snapshot, so yes, it's not a backup, but you have your snapshot state on the remote side. That's because it's maybe a backup, and it is a snapshot too. So you need to send your data somehow to the remote side. And the naive way is to use the great utility, for example, rsync. It's really great and it works well, and you may call it a day. But I hope that your remote side will be the true remote side, because you don't want to migrate to cloud this way. So the day finished, and we have the next day. We have the new data, and we may use the new backup here. And we don't want to create a backup with the same size, because our data won't be overwritten in a date at all fully. So that's why we want to make an incremental backup. And to do so, we need to check differences somehow. The naive way is to diff over files. Yes, you can optimize here. You can use metadata of files which have modified date here, and you may differ on only the changed files. But unfortunately, if a file was changed, you have to diff it all. Yes, we have some other layers of our usual storages which can build snapshots of our block layer. For example, LVM can do this. Yes, it will degrade your performance at a time, but it can do it. But the problem is that file system can't guarantee you that the exact block of your file will be at the exact place on your disk. That's why in the worst case, the size of your block storage snapshot will be the size of your old data, unfortunately. And let's look at ZFS here. In the initial backup, that's pretty the same, but you can use the built-in utility ZFS send. And you can send it not only at the usual storage, you can send it at another ZFS pool on the remote side. But after that, you should send the incremental backup. And in ZFS, to send a snapshot incrementally, you need only to read and send the different data, because snapshot is a pointer to different state. And we just send it, that's all. So the size is diff size only. Okay, let's speak about snapshots weight. The thing is that ZFS is not a file system. ZFS is object storage system in the first place. And only after that we convert our objects into the POSIX compliant file systems. That's why snapshots are snapshots of objects. So if you change only one block but do it billion times, then the next snapshot will have only this exact block. And that's why it's the usual case to have thousands of snapshots in ZFS in production. It won't affect your performance at all. But of course, we need to pay a price somewhere. And the price in ZFS snapshots are on deletion. You need to unlink all of your previous data. But you will unlink it after all, even without snapshots too. So the price is nearly constant for us. So I have another interesting question. Is your backup a backup? What do I mean here? When we have sent some bits to the remote site, we need to check somehow, can we restore from it? Yes, we can build some applications to restore it sometimes, build some and check some hashes, but it's additional utilities and scripts for us. And in ZFS, you can just ZFS send it to the remote ZFS pool and ZFS scrap it into the remote site, because the ZFS is the same on the remote site. And if you don't have any bugs in the realization, your data will be the same. There's another question. Usually we will rent our remote site because we want to make it cheaper. So we need to deal with compromisation question. And how can we deal here? And ZFS can help here too, because it has encrypted native encryption. And you can send your encrypted data without keys to the remote site, and you can check its hashes on the remote side too, because we have hashes of encrypted data, not an unencrypted one. So you don't need keys. You don't need to unencrypt data on the remote site at all. Okay, that's an interesting functionality, but functionality usually costs us somehow. And let's compare it with the usual way, with the usual Unix way. Do one thing, but do it good. It's a great paradigm, and I like it a lot. But the problem is that each of your layers should give you the same guarantees you want from your storage. So you want some ACID, like for example, atomicity. Major of your layers should give you this atomicity, unfortunately. And each layer will slow you down too. You can just try it. It will be an interesting experiment, and unfortunately, many already did so, and the speed is usually lower than ZFS. So the point of this presentation is ZFS knows about data, all about data. So you know which block of file lies exactly where on disks. And of course it has a price. We are a copyright file system. It costs us a lot to write additional metadata. We may deal with it somehow. We may compress it. It compresses flawlessly and greatly. But unfortunately, all of our writes are sequential, but all of our reads will be fragmented because of that. And we need to deal with some fragmentation somehow. Maybe look at one popular operating system and just defrag it. No, it's not a great way, because if you have some background job which will optimize your performance, then you will have the case when this job will work indefinitely, and you will have the position when your storage will stall because of that. And my mantra, and I hope this is the first one mantra, is your worst case should be your default case. So our writes are atomic too because of copy on write. Yes, it's more expensive, unfortunately, but we know our worst case and we work with it each day, and it's great. But we can deal with it. We can use a cheaper storage for our main pool, for example, but we need to deal with some metadata. We already discussed that copy and write, much metadata, we need more IOs for that, and we can remember about our special VDEVs. We can just offload all of our metadata on these nvme drives and call it a day. Okay, we need to remember that our reads are always fragmented, so we need some read cache. And the ZFS is pretty the same from the start here too, with, compared to other file systems. It has a less recently used cache too, but it's not all. It has a most frequently used cache too, and its cache ratio is more efficient, way more efficient than least recently used. Yes, it's more expensive, but it do a job well. And you can offload your caches on stateless NVMe drive too. So you can grow your RAM with NVMEs. Okay, there's another problem. We already discussed that each of our writes are the same as git commit. And if you know, git commit, it's not so fast, unfortunately. So every our write will be slower by default. And we need to do something with synchronous writes. We should optimize it somehow. And any of ZFS pools will have journal for this. Its journal is used not for consistency, it's used only for synchronous write, temporary write. So we can just offload it to fastest NVMEs we have, and it will be pretty fast. Okay, we have some storage. It has many blocks in it, so how to manage it, because we want to do it well and fast. And let's go back to the example with database. Usually databases consist not only data blocks, which usually have random I/O and have small block sizes, for example, 4 or 8K, but they usually consist of val logs too, write ahead logs. They are written sequentially, and we can make a profit from it. We can set a larger block size, so it will be compressed more efficiently, etc. And there is another case. We can use some files in this storage too, blobs, and they will be more sequentially too. But the problem is we have one array, and you can't set it to be optimized for different I/O patterns, unfortunately. In the worst case, you have to build different arrays with diadem, etc., and give it to other parts of your system. And in ZFS, there is an interesting thing which is called as a dataset. As a user, you can call it a directory, an analog of directory in ZFS. So it's cheap to create. It is visible to operating system as file system. And the main point is that you can change any of its configuration. You can change its block size. You can change compression type. And if your block is larger, then your compression will be more efficient too. You can make snapshots of different datasets, and you don't need to snapshot a whole pool for that. And you can make different consistent datasets or snapshots across them. So your data blocks and val logs will be consistent here in your snapshot. You can encrypt some part of them. You can even ignore some synchronous write of some of them if you want to lose your several seconds of your synchronous write at the expense of more speed, and etc. I want to highlight you a compression question, because some of you can tell me that compression is slow, why don't we even talk about it? But the thing is, in the wild, you can see that your val logs may be compressed from 3x to 100x. So you will have less IOs because of that. And there are many modern compression algorithms which are really fast nowadays. For example, LZ4. It's per one thread, you can compress data with a speed of 800 megabytes per second and decompress them at the speed of 4.4 gigabytes per second. And it's just several times slower than memCPI. And on uncompressible data, it will speed up. It knows how to work with it. And the fun fact, I saw a case where we had more than 1,000 compression ratio. It was an interesting case with hosting provider. It was fun. And I have a last question for you. We have file systems which guarantees our consistency of our data. And do we still need val logs in our databases? There is a nuance, of course. The nuance is that we use our val logs not only for consistency now, but for other many things. But it's an interesting topic to discuss too. And I hope that I could show you why I think that ZFS is a Swiss knife in file system world. Yes, you won't cut your bread with Swiss knife, so there is no silver bullet yet. But you can just install this non-default file system in major distributions that it will work from the box. So the main point is experimentation. Please experiment. And we have a great community of people. And this community consists not only from companies. It consists of people which not work with ZFS at day. They work with ZFS at night too, which is really fun. Which is really fun, because there are people not only from ZFS world. There are people from Linux kernel world. There are people from systemd world, etc. And the thing is, yes, we have to write our file systems in C language because it's really fast. We have our kernel model written in C. But there are many other things which are written in different languages. We have many frameworks, we have many tests, we have many documentations after all. And as documentation maintainer, I'm be really glad to help you here if you want to contribute something. So I hope you liked it. Please give your feedback, it's precious for me. You can find my contacts, you can find some community links, and you can find link to the slides too. I'm ready to answer your questions.
So thank you very much. Thank you. Raise your hand if you have a question.
Thank you for the presentation. Amazing. I got a lot of interesting information. The question is, you told about defaults that they are not good in many cases. Is there any guide or any information source which I can use to understand which defaults should I use? Like block sizes and I know some configurations.
Yes, in our documentation, which will be the first link on our GitHub repository, you can find the page about benchmarks, best practices, and etc. And they are good not only for ZFS file system, but for other systems too. But in other file systems, you usually can't change many of them, unfortunately.
I would like to have something like quick start guide, which you can just follow and get the best options for you. Is there anything like that?
The thing is, if you want a quick start guide and you don't want to think about something, then the defaults will fit you. That's great.
Got it. Okay.
I can give you an example. We have a block size of 128 kilobytes. That's pretty large, you may think. But on the latency of hard drives or even on the latency on NVMEs, we want price much more latency because of this prefetching. And that works very well.
I think it might be related to some certain cases, like you could use this block size for sequential writes, or this amount of block size for virtual machines and some options.
This page which I discussed before, it is exactly a page you
represents
want.
that. Okay,
Yes.
got it. Thank you.
Yes, please, over here.
Hello. I haven't used ZFS in a while, so I'm interested in how much overhead do you think it has now on modern disks and systems in like writing all the metadata and the structure and snapshots and everything?
We can speak about the rule of large finger, or I don't know how it is in English. You should expect nearly half of read performance on fast storage, and you should expect write gains on some storages too, because while all reads are random for us, all writes are sequential for us because we group them. So on hard drives, it will be really faster than other things. In NVMe drives, unfortunately, there are cases which we should optimize for now, and we won't give you full capacity of NVMe speed. For example, if you want to build 10 NVMe drives full, etc. That's because we have a pretty efficient ARC cache here, but unfortunately, it costs us something, and any read or write won't be copy-free, unfortunately, for now. Okay.
We have a question here to the right.
Okay, suppose we have Microsoft SQL Server on Amazon system. It's run on Windows. Can we use this system for replication of the database, like hot worm replication? If one node is dying, we have replicated data on other location and can restore there.
With snapshots, you can make asynchronous replication. So you will have some seconds, for example, a difference, but it will be replication, but asynchronous one.
But did you try it with SQL Server?
For SQL Server, no. There is a fork for Windows with ZFS 2. I don't try SQL Server on it yet, unfortunately.
Thank you.
Yes, question in the center, please. Any more hands, please? Do you have? Please
Hi.
raise.
Hi.
Thank you very much for your presentation. It's always fun to watch some presentation, not very dry, but with some nice pictures and some fun stuff. My question is related to backup. You mentioned that ZFS have incremental backups, but does it have some deduplication algorithms that could decrease backup size even further?
It has degradation, but it will cost you your RAM size. We have synchronous deduplication here, so on each write, if you enable deduplication, you have to see in your deduplication table and compare if we have already this block. So your deduplication table should be in RAM for that. Otherwise, you will have major degradation of performance. You can offload it on special virtual devices, which will be NVMEs. And if you're ready for that, it will work, yes.
Sorry, this table is...
Mick, please.
Yeah, I'm so sorry. Should this table be on the source or on destination?
It will be on both of them.
Thank you. Another question over here.
Thank you. So I have somewhat of a silly question. It's like, let's say I'm sold and I want to try this thing, and like I have a laptop with Linux that I use every day and I can try and install it there, but I read different opinions about that, and most of them are telling that it's probably a bad idea. What do you think of that? Like, can I just install it and use it for everyday cases?
You can. My laptop works on ZFS only. It's Linux, it's ZFS only, and it works really great. I have a compressor nearly 1.5, and I ignore any synchronous writes. It helps me a lot too, because that's the local file, the local node, the local file system, and I didn't care about it, and I liked it a lot. That's why I'm a fanatic of ZFS, after all.
Okay. Thank you.
Any more questions? We have 10 minutes left, at least. We have a pair of socks for the best questions, so that will keep you warm in these sunny days. So please raise your hands. 1, 2, 3. I have one. That might be the silly question. I'm the guy with it. Yeah, I am here. So you told us that openZFS is perfect, is good, and excellent. And I'm sold as well as a colleague over there. Is there any edge cases where openZFS is bad?
So I can describe ZFS as a universal file system. It's good when you don't have a really edge cases, when you need all of your performance from your NVMe drives, or etc. Or you build a large cloud where you need to backup on the certain level, on a certain layer. But for the usual case, if you want to build some default storages, then ZFS is a great example as a default file system for the home NAS, for examples.
Okay, I see. So,
sorry, I want to add, many of businesses around ZFS is database businesses. So ZFS is pretty great besides database too. You should optimize it, of course, but it's really great too.
Okay, thank you. Andrei, please.
I have the mic, so I can maybe drop in.
Okay.
Are you aware of what AWS does with EBS? Because the features seem really, really similar. I'm not sure if they took this as inspiration, or you have backups, you have snapshots, you have all the structure that you have in ZFS. Maybe they're reusing the code from the project, or just took it as inspiration.
Unfortunately, Amazon don't want to tell, at least I didn't find any information about the underlying storages, and that's a pity. I really want to know that. But there is an interesting example where they use ZFS for all. They are called shared storages. So when you need a performance of local storage, but you can go to it via NFS. For example, if you render something and you don't need a clustered file system, it's pretty great, and they declares nearly 1 million IOPS from that, and nearly up to 15 gigabytes per second from that. And that's an interesting case too. They have just announced it half a year before.
Yeah, I have just a short question. You told that you use it in your laptop,
Yeah.
and your laptop is using it on top of NVMe.
NVMe, yeah.
Yeah, just thinking that ZFS was invented for optical drives first, and I think it has best performance for optical drives. I'm curious on which state is it for single drives use, like for NVMe, for single NVMe drive? Because I heard that you told 4 drives is already not so good capable to. There is
For
bottleneck.
expensive
Yeah,
NVMe
yeah,
drives, production ready. Yeah.
Aha, got it. So for standard usage, like for consumers' needs, you can use it.
With NVMe, yeah.
Yeah,
Yes.
and it will utilize it fully.
First thing is much of NVMEs are not so fast after all, unfortunately. I hope that it will be faster, but no, unfortunately. And many NVMEs will degrade up to the point then they may be slower than hard drives too, unfortunately. But about optimization for solid-state drives, yes, there are optimizations for it. We know which disk is rotational or non-rotational, so we can schedule, make our scheduler more efficient here for fragmentation after all. And we have discard too, because some NVMe drives will give you pretty worst performance if you don't discard them periodically. Oh, yes.
And how discarding when you say that it's always keep all the data?
We know which of our underlying storage is not used, so we track all our existing data. That's why, that is why when you create ZFS pool from scratch, it will create nearly instantly, because it just tracks what it knows about. It should not allocate all of your disks. When you create mirrors from MD-ADM, it should initialize disks. But we don't need it here. So we track, while we track just what we have, and while we alt and we filled all of our data, we track just what free space do we have. So it's pretty efficient here. And because of that, we know that these blocks are not used now, not for snapshots, not for main data. And yes, we just issued a blockade discard for them.
Thank you. Very clear.
Thanks.
Hello, thanks
Hello.
for presentation and ZFS. I am ZFS fan too.
Hello.
But when I
Yeah, please.
when I use ZFS send on compressed ZFS, I must
will decompress your
I
data
must
by default,
compress again. And no, ZFS decompressed, but I must compress when ZFS can send compressed data.
Yes, you just need to add big L argument, and it will send raw data, not decompressed.
Ah.
The fun part is when I told you about this compressor ratio, we found it in this exact case when man tried to send data to a remote site and backup it, and he saw. My client has 2 gigabytes of data. Why ZFS sends 2 terabytes of data? What the heck?
We use ZFS on under database and get 8x compressed.
Oh, great. I like these cases.
We do.
Thank you.
Thanks.
Thank you for your talk. A little bit more questions about ZFS on NVMe. So you told you use it on your laptop. And if we speak about normal consumer NVMEs, they're usually limited to write cycles, after which they die, and to the size of the storage.
Yeah.
They're usually not really huge. So if we compare ZFS to some normal Linux file system on consumer laptop, What is the difference with these parameters? Write cycles it will use and space it will consume comparing to
It's called
normal.
write amplification, and it differs a lot here. Yeah, if you have large blocks and you will try to make a random I/O of 4 kilobytes on them, then you will inflate your writes nearly tenfold. Unfortunately, yes. But nowadays, the usual laptop NVMe is pretty good, even for the with this write amplification. You will have problems with firmware or exact manufacturer than the problem with writes from ZFS here. Because after all, it's a laptop. And so my writes are not so large. Plus I ignore synchronous writes and I optimize here. I can make my dirty buffer to write less frequently. For example, one time in 100 seconds, for example, and another ways. So we can deal with it, but yes, the write amplification will be here if you don't set your block size exactly to your I/O pattern block size. Sorry.
But you usually don't have some specific write pattern if you just work with your laptop. It's not.
Yes, that's why defaults are really great here. I don't have any problems. We can look at how much data I have written in a year on this disk if you're interested, just after the questions. That's no problem.
Okay, thank you.
Thank you very much. I think we're done. George, it's up to you to decide who asked the best question.
I like the questions from this man.
Okay, so welcome our hero. And thank you very much, George, for the talk. We have a present for you. Grab it.
Please
don't
review
forget.
and feedback. That's really important.